Okay, let's give it 1 minute. Wait for some other people to come. How are you all finding the course so far? Is it okay? Is it understandable?
Yeah, it's okay.
Do you have any questions from the previous 2 lectures? Or from some of the extra reading material that I had recommended?
Professor, I haven't done mathematical induction earlier. I found that a little tricky to understand.
Sorry, what have you not done before?
Mathematical induction, which I found on in the chapter for sequences and series.
Induction. Why do they use induction over there? 1 second. Can you tell me which part of that booklet they discussed induction in?
To extent, I'll just like.
Is this in 11.8?
Yeah. 45th or something, the PDF page.
Right. I mean, yeah, if you want to read it, that's great. But I didn't intend for you to go beyond 11.7. I think I have specified that on the.
Oh, cool. Okay.
But if you want to discuss it, sure. Maybe in the office hours or sometime later, if you want to talk about it, I'm happy to discuss it with you.
Sure. Thank you.
Any other questions? Four, 12, 13 people so far. Okay, anyway, let's start. It's 10:33 already. Okay, great. So where's the board? Right. So let's start with a quick recap of what we did last time. What did we do last time? We discussed functions. And we saw that functions can be one-to-one maps or many-to-one maps. And they can also be classified into functions and onto functions. Then we went on to a discussion about vectors in 2 dimensions or 3 dimensions. So you can write a vector in general as some ai plus bj plus ck, where the I, j, and k are unit vectors along x, y, and z axis. And a, b, and c are the 3 components of the vector along each of those directions. Then we saw how to add and subtract vectors. We saw that if you want to multiply 2 vectors, you can either define the dot product or the scalar product. And you can also define the cross product or the vector product. As the name suggests, this gives you a scalar, this gives you a vector. Okay. What else did we do in vectors? We saw what is the magnitude of a vector. Or the length of a vector. Then we went on to a discussion about matrices, which are just boxes with m rows and n columns containing various elements. We saw that if n is equal to 1, so an m cross 1 matrix, it just looks like a column with m rows. And in fact, you can think of a vector as a 3 cross 1, three-dimensional vector as a 3 cross 1 matrix with elements A, B, C. You can, instead of writing a vector like this, you can also write a vector like this. Of course, with the understanding that first component is always going to be X, second component is always going to be Y, third component is always going to be Z. Then we saw matrix multiplication. Where you multiply one m cross n matrix with an n cross p matrix, where these two have to be the same. And you end up with an m cross p matrix. So this is what we discussed last time. I'll ask you one more time. If you have any questions, we can discuss. Otherwise, then I'll go ahead. So anyone? Like, we're mostly discussing just things that most of you have studied in your 11th and 12th standards. So maybe there were some things back then that you didn't understand and you just went on with it because in the end you had to get points in the exam. So now's your chance. Probably your last chance at asking physics and maths questions. Okay, then we'll proceed. So there's one very interesting property about matrix multiplication. So suppose I take two matrices. If I, let's take some small numbers, 1, 2, 1, minus 1. So this is a 2 cross 2 matrix. And I'll take another 2 cross 2 matrix. 2, minus 1, 3, 4. Now if I multiply A and B, what does this become? 8, minus 1 and 8 is 7. 2 minus 3 is minus 1, minus 1 minus 4 is minus 5. Please do this yourself and verify, because sometimes I make stupid mistakes. But then if you change the order and multiply, so and you see that these two are not the same. So AB is not equal to BA. So we say that in general, matrix multiplication is not commutative. which means that the order in which you multiply two matrices is going to be very important. You cannot just flip the order of them. If you've been asked to multiply them in a certain order, then you have to maintain that order in order to get whatever required result you need at the end. So non-commutativity of matrices, which is very different from what we see in, let's say, real numbers or integers, where if you multiply them, it doesn't matter what order you multiply them. However, matrix multiplication is associative, which means that if you're multiplying 3 of them, then it doesn't matter which 2 you do first. So this is the same as this, but the order is still the same: ABC, ABC. You cannot suddenly make it CBA or BCA or something. That order has to be maintained. But as long as you have maintained the order, whether you do these 2 first or these 2 first is immaterial. We can also, wait, should I do? Okay. Now we have already discussed determinants before. And what we can do is we can take the determinant of a matrix. So for example, just using this A and B over here, determinant of the matrix A is 1, 2, 1, minus 1, which is given by first you multiply these 2, then you multiply these 2. So 1 times minus 1 is minus 1, subtracted 1 times 2 is 2, which is minus 3. So if you have a matrix whose determinant is 0, suppose the matrix is called M and its determinant is 0, then M is called a singular matrix. And if the determinant is not 0, then it is a non-singular matrix. And we will see why singular and non-singular is important in a minute. So last time there was a question, why do we need to use vectors and matrices and things like that? So I'll give you some examples of where we use these things. So one of the most common uses of matrices is in solving systems of linear equations. Well, what do I mean by systems of linear equations? Suppose I have some equations: x plus y equals 2, 2x minus 3y equals minus 5, and I ask you to find x and y. Now normally, so these are 2 equations and 2 variables. Now you have been doing this kind of calculation since school, and there are easy ways of doing this. But suppose I had 3 equations and 3 variables, 4 equations and 4 variables. If I go to higher number of unknowns, the system becomes more complicated. And then it becomes, it's not straightforward to use your school type methods to solve these equations. So then it's convenient to use matrices. So let's take one example and see how we use them. So the example I'm using over here is, it's 3 equations and 3 unknowns. X minus 3y minus z is 5. X minus 2y plus 3z equals 6. So these are 3 equations in 3 unknowns, x, y, and z, and I want to solve them and find the values of x, y, and z. So what I do is I first write these 3 equations collectively as a matrix equation. So how do I do that? If you look at the left-hand side, the three equations, you can write it in this form. So here is a column vector x, y, z containing the three unknowns. Here is a matrix in which I'm going to put the coefficients. So in the first equation, coefficient of x is 2, coefficient of y is 1, coefficient of z is -2. Second equation, coefficient of x is 3, then -3, and -1. And in the third equation, it's 1, -2, and 3. And you can see that if you do a matrix multiplication of these two, you will exactly get the left-hand side. So you will get 2 times x plus 1 times y plus -2 times z. So that's the left-hand side of the first equation, and so on and so forth. And on the right-hand side, again in a column matrix, I will put the right-hand sides. So -1, 5, 6. I hope this is clear. This matrix equation is nothing but these three equations written in a slightly different form. Now I want to introduce three properties of matrices that are called elementary row transformations. If you have a matrix equation like this, you can do elementary row transformations without changing the meaning. What are the three elementary row transformations? First is you can exchange any two rows. What this means is I can write the same equation as before I do this, I should define something called an augmented matrix. An augmented matrix is just this big matrix over here, and then this smaller column matrix stuck to it. So in this case, 2, 1, -2, 3, -3, -1, 1, -2, 3. And then you just put one line over here in between to distinguish the two sides. And then you stick that right-hand side matrix over here. So this is called an augmented matrix. Now I'm going to introduce my elementary row transformations. The first one is exchange any two rows. So for example, over here, I might call this So I've basically interchanged the second and the third rows. And that's okay. The meaning of the equation still remains the same. The second row transformation I can do is I can multiply any row by a constant, by a number. Okay. So again, coming back over here, suppose I decide to multiply the first row by a factor of 3. Then I can write this as And the third thing that I can do is I can add or subtract one row to another. So over here, suppose I decide that I want to add the second row to the first row. So the first row now becomes first row plus second row. So this becomes, in the first row, I will get 2 plus 3, 5, 1 minus 3, 2, minus 2 minus 1 minus 3, minus 1 plus 5 is 4, and everything else remains the same. So these are the three elementary row transformations. And if you use these, the meaning of the three linear equations remains the same. These three rules are valid no matter what your matrix is. If I give you if I give you 100 equations with 100 unknowns, you can still use these three elementary row transformations to solve these equations simultaneously. So, any questions so far?
Is there any particular criteria with respect to the dimension here or not?
So, if you want a proper solution, then the number of variables must be equal to the number of equations. If you have 3 unknown variables, then you must have 3 equations in order to be able to solve them. If you have 3 variables but only 2 equations, you will not be able to solve them, right?
Yeah.
So because of that, this matrix over here, this one, will always be a square matrix. Because number of rows corresponds to how many equations you have, and number of columns corresponds to how many variables you have.
Yeah.
So this will always be a square matrix, and the augmented matrix will always be square matrix but with one extra column in the end. Any other questions? Okay, so let's try and solve this set of equations using these elementary row transformations. So the first trick to do, okay, so the idea is when you have a matrix like this, always try to bring the number 1 along the diagonal and always try to make everything under the diagonal 0. If you do that, your life will become very easy. That is the trick. So we'll use the following. First, try to make, let's use a different color. I want to try and make the number over here 1. How should I do that? The simplest thing to do is to exchange the first row and the third row, because then I will get a 1 over there. So let's do that. First, I will interchange first row and third row. So I get 1 minus 2, 3, 6. Everything, the second row remains unchanged and the first row has come down. Good. Now, so I have a 1 in the top left corner. Now I'm going to try and make these two fellows 0. How can I do that? I can say, since I can always multiply a row by a constant, and I can always add and subtract rows from one another. So I can say, suppose from the second row, I subtract 3 times the first row, because then this 3 over here will become 0. So I get 1 minus 2, 3, 6. 3 minus 3 is 0. That's why we are doing this. Minus 3 plus 6 becomes 3. Minus 1 minus 9 becomes minus 8. 5 minus 18 is minus
Professor, I had a doubt.
10.
I did not understand what happened to the fourth column. How -156 changed to 65 -1. Do we have to invert it as well?
Whatever you have to do it to the entire matrix, including what's happening to the right hand side. The 3 elementary row transformations you have to do throughout.
Oh, okay.
Does that answer the question?
Yeah, I think so. Yes.
I mean, it's just a tool. Basically, you have added up, you have attached the right hand side matrix to your main matrix and made the augmented matrix. And now these row transformations you're doing on the augmented matrix.
Okay.
So whatever you're doing on the left part, you are also doing on the right part.
Okay. Okay.
So now I have got a 0 over here. I want to also get a 0 over here. So I can do a similar trick. From the third row, I will subtract 2 times the first row so that this fellow becomes 0. So then, 2 minus 2 is 0. 1 plus 4 is 5. Minus 2 minus 6 is minus 8. Minus 1 minus 12 is minus 13. Why am I getting such similar numbers? Have I made a mistake? No, no. I hope somebody is doing this independently and checking my thing.
Professor, I still didn't understand like the step 2 and 3. Can you just like explain one again?
This one?
Yeah, either of them, any one would do.
So I'm combining rule numbers 2 and 3. Okay, so let's say I start over here. In the first column, I have a 3, which I want to get rid of. I want to make it 0.
Yeah.
So if I multiply the first row by 3, then the first row will become 3 minus 6, 9, 18. And this, if I subtract from the second row, then since the 3 is over there, then 3 minus 3 will become 0. So that's the reason why I'm multiplying the first row by 3 and subtracting it from the second row.
Okay, but it doesn't still affect the existing first row. That would remain the same.
So think of it this way. First, I multiplied the first row by 3. Then I did second row minus first row. And then I multiplied the first row again by 1/3. So first row again goes back to what it was.
Okay, fine.
Any other questions? Okay. Let's write down that equation we had. Can someone just read out the numbers to me so I don't have to go back and forth?
-2, 3. Oh no, sorry. That's 3 and 6. 3 minus 8 minus 13.
3 minus 8 minus 13.
5 minus 8 and minus 13.
Okay, thank you. So remember that in the end, we want something of the form 1, 1, 1, 0, 0, 0, ideally. So now the next thing we will try to do is we will try to get a 1 over here. Any idea how should I do that? One way would be I can, to the second row, I can add the first row, because then 3 minus 2 becomes 1. But the problem with that is then the 0 will become 1. I don't want that. I have already, with great effort, I have made that 0. I don't want to change that. So I will not do this. Instead, I will do, you multiply the second row by 1/3. And now the numbers become dirty. Now, how should I make this 0? In fact, I can make this 0 and I can make this also 0. Life will become even better if I can convert this matrix into an identity matrix with 1s along the diagonal and 0s everywhere else. Any idea how I should do this? Suggestions, anyone? How about if I do first row plus 2 times second row? So my second row doesn't change. To the first row, I'm adding twice of the second row. So 1 plus 0 is 1. Minus 2 plus 2 is 0. 3 minus 16 by 3. 9 minus 16 minus 7. And 6. How much is 18 minus 26 minus 8? And I'm just doing one more step in the same one. To the third row also, now I will subtract 5 times the second row so that this 5 becomes 0. So now 0 minus 0 is 0, 5 minus 5 is 0, minus 24 plus 40, 16. And minus 39 plus 65, 35, 36, 12. $49, 59, 26. I feel like I'm making a mistake somewhere because I don't think these numbers are supposed to be so annoying. Are any of you trying to do this independently on your own? just to check if I'm making a mistake.
Could you go back to the last slide?
Huh?
Yeah, the second step, the third column, I guess, minus 1 times minus, I'm sorry, minus 1 minus 3 times 3, which becomes minus 9 minus 1, should be minus 10 instead of minus 8.
Where?
The second
From here
step,
to here?
yeah, it's
Second row.
minus 1 minus 3 times 3, the third column.
Minus 1 minus, oh, minus 10.
Yeah.
Okay, yeah, now you tell me this. Okay, this doesn't change the second row. So now this is 3 minus 20 by 3, which is minus 11 thirds. And minus 8 plus 50 by 3. Okay, this looks a lot better. Thank you. Now I want to get a 1 over here. Any ideas how I should do that? I can just multiply by 3 over 26. Third row multiplied by 3 over 26. So 1, 0, minus 11 third, 0, 1, minus 8 third, 0, 0, 1, 1. Now, how should I get rid of these people and make them 0? Same way we've been doing all this time. So to the second column, to the second row, I will add 8 by 3 times the first row. And to the first row, I will add 11 by 3 times the third row. Third row. So 1, 0, 0. So in the second one, it is minus 13 by 3 plus 8 by 3. I think there is still a mistake somewhere. minus 8 by 3 plus 11 by 3 is 3 by 3, which is 1. I feel like there's a mistake over here. Homework, find the mistake. Anyway, so just to tell you what we have managed to do. Now this is our augmented matrix. Let's try and break it up again into the way it was before. So this has now become 1 0 0 0 1 0 0 0 1 x y z is equal to 1 minus 5/3 1. I mean, this minus 5/3 is probably wrong, but whatever, there's some number over there. And now if you do the matrix multiplication to this and get back the original equations, you'll see that this is 1 times x plus 0 times y plus 0 times z. So that is x. And on the right hand side, this is equal to 1. Similarly, from the second row, you get y is equal to minus 5/3. And then from the third row, you'll get z is equal to 1. So by doing these elementary row transformations, we have managed to solve these linear equations in 3 variables. You can have 7 equations in 7 unknowns, 12 equations in 12 unknowns, whatever. The exact same procedure you will follow. Always first try and get this fellow to become 1. Once this has become 1, you use this 1 to make these 0. Then you make this fellow 1 by dividing the second row by the appropriate factor. Once this has become 1, you can make these two 0. Then you make this element 1 by dividing by the appropriate factor. And using this, you make these two 0. That is the general procedure for any kind of elementary row transformation in order to solve these linear equations. Even if it's a bigger matrix, even if you have 4th row, 5th row, etc., you will use the same thing. In the end, all your diagonals have to be 1, all the off diagonals have to be 0, and then basically you will get some nice solution like this. Any questions on how to use linear equations to solve, how to use matrices to solve linear equations? Okay, if not, let's take a 3-minute break. Okay, so this is how you use matrices to solve linear equations. Okay, why should a biologist care about doing this? So I have written down a biology example for you. So there is something called, how much time we have? Around 40 minutes. No? So there is something called the Leslie model. Is this something that you do in your 12th standard in biology? I don't think so.
No, I haven't heard of this.
Okay. So what the Leslie model describes is when you're going from in any population of a particular species, of a particular organism, as you go from one generation to another, how does that progression take place? So, for example, suppose we are looking at some plants, and at time t, well, by time I mean generation t, suppose the number of seeds is ST. The number of seedlings is NT. The number of young plants is YT. And the number of adult trees is AT. Now at each stage, whether it's at the seed stage, at the seedling stage, at the young plant stage, or at the adult tree stage, suppose we say that there is a probability, how should I put this? So for an individual to stay in the same stage, the probability is P, and to advance to the next stage, the probability is Q. So for example, if you say what is the probability that a seed advanced to the seedling stage, then that is going to be PS. What is the probability that a young plant, PS is the probability that a seed remains a seed, it doesn't advance to the seedling stage. What is the probability that a young plant grows up and becomes an adult? That is QY. And these are some numbers that, let's say, they are known to you. You, based on various experiments, you have already got these numbers experimentally. And in addition to these, the plants and the trees produce seeds as well. So number of new seeds produced by young plants we call it, let's say, Fy, and the number of new seeds produced by adult trees is Fa. So this is all the data that is given to you. And now I want to ask you the question, how many seeds, seedlings, etc. will you have in the next generation? So you know what is happening at time t, what will happen at time t plus 1? That is a question that you want to ask. So then we set up our equations as follows. How many seeds are there in time t plus 1? First of all, there were some seeds from the previous generation t which remained in the same stage. So that is St times PS. Seeds from the previous generation which with probability PS they stayed in the same stage as seeds itself. But seeds also came from here, from the young plants and the adult trees giving you seeds. So how many young plants were there? There were YT young plants, and each of them gave FY seeds. And there were AT adult trees, and they gave FA number of seeds. So in the next generation, this is the total number of seeds. How many seedlings are there in the next generation? There are some seedlings from the previous generation which stayed as seedlings. Number of seedlings in the previous generation multiplied by probability of staying in the same stage. But there were also seeds from the previous generation which advanced to the next stage and became seedlings. QS, because Q is the probability of advancing to the next stage. And seedlings don't come from plants and trees and all, so that's it, nothing else over here. Are you following me so far? I'm writing what is happening in the next generation in terms of what was already there in the previous generation times the probability of certain things happening, of either staying in the same generation or advancing to the next generation. How many young plants are there in the next generation? Well, there were some young plants from the previous generation which stayed in the same generation. But there were also seedlings from the previous generation which advanced and became young plants. And similarly, the number of adult trees in the next generation is equal to the adult trees from the previous generation who stayed there plus the young plants from the previous generation which advanced. So now these are my 4 equations, and I want to try and write them down in matrix form. So I will say S t plus 1 n t plus 1 y t plus 1 a t plus 1 is equal to something times what was in the previous generation. And these coefficients you can read from these 4 equations. So st plus 1 is ps times st, nothing times nt, fy times yt, and fa times at. These come from the first equation. From the second equation, nt plus 1 depends on st with a factor of qs. It depends on nt with a factor of pn, and it doesn't depend on anything else. Yt plus 1 doesn't depend on st, depends on nt with a factor qn, depends on yt with a factor py, and doesn't depend on at. And at plus 1 doesn't depend on this, doesn't depend on this, yt with a factor qy, at with a factor pa. Are you with me? Can you see where this matrix came from?
Yes, Professor.
Is there something that you would like me to repeat? Okay, so this matrix equation, suppose I write, so this is like, let's give it some name. So let's call this as this column matrix as x t plus 1. Let's call this column matrix as xt, and let's call this big matrix M. So what I'm saying is that x t plus 1 is M times xt. This is my matrix equation. The elements of M are known from previous experiments. You know in every generation how many, like what fraction of the seeds become seedlings, what fraction of the seedlings become adult trees, and so on and so forth. How many seeds does every adult tree produce? All these things you know. So this equation will tell you, of course, this is a very simplified model. There are lots of other factors. Somebody goes and cuts a tree, etc., etc. But in a very simplified model, this is how you can model the progression of generations. Why is this useful? Now, what if I ask you, what happens in the next generation? What happens in t+2? So then you can once again say, now this is going to be m times xt+1. But xt+1 is m times xt. So this is m times xt. So this is m square xt. In general, if you want to know what happens in the nth generation, this is going to be m to the power n times xt. So as long as you know the numbers in your first generation and you know the elements of the matrix M, you can use this to find what is happening in any future generation. That's why this is a useful tool. You can also do the inverse problem. Suppose you know how many seedlings, etc. you have in the next generation, and you know all these numbers. You want to know how many are there in the current generation. Then that also you can find out. Then this is just a question of solving 4 equations and 4 unknowns, which you use the same method that we did before. And you can find out how many of each type are there in the current generation. Any questions? This is just one example. There can be numerous other examples of uses of vectors in biology. Okay, so the last thing I want to discuss in the topic of matrices is inverse of a matrix. So suppose you have some matrix M. Question is, M times what will give you the identity matrix? Have I discussed identity matrix with you? Did I tell you last time what the identity matrix is? If I didn't, the identity matrix is just, what happened there? I think I lost connectivity for a bit. Are all of you still there?
Yes,
Yeah.
Professor.
Okay. How much did you see and hear?
You were asking us if we knew what an identity matrix was.
Okay. So an identity matrix, and this is in the context of square matrices, is when you have ones along all the diagonals and zeros everywhere else. So this is called the identity matrix because you can see if you multiply this identity with any other matrix, you will get back that same matrix. So it's like the number 1. It maintains the identity of any matrix. And just as in numbers, if x times something is 1, then that something is the inverse of X. Similarly, over here, I want to find what is the inverse of a matrix M. And the way for that is also straightforward. You again use elementary row transformations. So I say, suppose M times X is the identity matrix. So you write down your matrix M, whatever. Shall we take an example? Let's take an example. Suppose I want to find the inverse of, I'm going to take a simple one, 1, 2, 0, 1. So here's a 2 cross 2 matrix. I want to find its inverse. So I will say, okay, let 1, 2, 0, 1 times X be the identity matrix. Now, once again, you do those kinds of elementary row transformations to try and turn this one into identity. So first, I want this element to be 1. It already is. Then I want to make this element to be 0, which it already is. This is too easy. Let's find the inverse of this one. So 1, 0, 2, 1. X is 1, 0, 0, 1. So this element is already 1. Okay. Now I want to make this one to be 0. So I will do second row minus 2 times the first row, so that this becomes 0. So I get 1, 0, 0, 1, X. And of course, I must do the same thing on this side. 0 minus 2 times 1 is minus 2. And 1, 1. So this is just I times X is 1, 0, minus 2, 1. Or X is 1, 0, minus 2, 1. So X, which is the inverse of this matrix, is just this. So that's how you find the inverse of a matrix. The important thing to remember is that you can only find the inverse of a matrix if that matrix is non-singular. So this determinant of 1, 0, 2, 1, this original matrix of ours, is not 0, which means it is not singular. That's why we can define what is the inverse of this matrix. Any questions on matrices? If not, we will go on to discuss derivatives now. So I'm going to start with an example of motion. So when something is moving, you can, and I'm just saying moving along in one dimension. So here is the real line, 0, 1, 2, blah, blah, blah. And I call it X. So if there's a person walking along the X-axis, and they have some certain speed with which they're moving at. So what I'm going to do is I'm going to make a plot of how they are moving as a function of time. So let's say when time t is 0, they start over here at the origin, and then they are moving. The graph of their position as a function of time is given, let's say, something like this. So what does this mean? So as time goes by, so after 1 second, they were at x equal to 1, let's say. After 2 seconds, they were at, let's say, x equal to 2.3, and so on. So they kept moving towards the right, but then at some point, X started to reduce, means they started to then move towards the left. And then again, from this point onwards, they start to move towards the right. So whatever, they could have moved in some very complicated manner. This is the graph of their position X as a function of time. And now suppose I want to find out what is the speed, the average speed with which they were moving. So the average speed with which they were moving is going to be the distance that they traveled divided by the time that they took to travel that distance. So where should I choose this average speed from? Suppose I say from this time to this time. So how much distance did they travel? They traveled a total of this much distance in this much time. Well, delta x, the difference between these two, and delta t, which is the difference between these two times. You can think of it as having drawn a triangle over here. This side of the triangle is delta x. This side of the triangle is delta t. So delta x divided by delta t gives you the average speed with which this person is moving. But you see, this value is going to keep changing depending on what interval I take. So delta x over delta t, you can see, is the slope of this line. But the slope changes depending on what 2 points I take. Suppose I had taken this point and this point instead, then this has a different slope. If I had chosen this point and this point, then I would get a different slope. So the average speed is going to change depending on what interval delta x and delta t I choose. So the best way to define a speed is to define it not over some large interval, but to define it over as small as interval as possible. So if I ask you what is the speed over here, can you see that? Is this visible? Yes. If I ask you what is the speed over here, then it's a good idea to not take a big interval, but to actually take a very small interval over here. Or if I ask you what is the speed over here, then just take a small interval over here. So what we say is that the speed is delta x divided by delta t, but when you're taking a very small interval. So we say when delta t is very small, almost going to 0. And this we denote as dx by dt, or we call it the derivative of x with respect to time. So I said, let's say this curve looks something like this. How does the derivative look? So derivative is just the rate at which this is changing. So initially, when t is very small, you can see over here that x is just increasing at a constant rate. So this has some constant value, constant, doesn't change. As you move up over here, the rate at which x is changing keeps on decreasing until we reach this maximum point over here. At this maximum, x is not changing at all. So that means the derivative is slowly becoming 0. So think of it as coming down like this, coming to 0. Then in this region, you will notice that x is actually decreasing with respect to t. As time goes by, the value of x is going down, which means that the rate at which it is changing is becoming negative. At this point, again, x as a function of time has become flat. It is not changing over here. So the derivative becomes 0. And then over here, once again, x is increasing at a constant rate with time. So maybe constant. So the derivative of this function looks something like this. That is what we mean by rate of change. Any questions about what derivative physically means? There is, how much time we have? Around 10 minutes, no? I'm going to put in the chat over here a link to an online simulator. In general, this website has lots of good simulations if you want to visualize things in maths, in physics, in chemistry, in biology. So you'll find lots of good tools over there. Some of them are aimed at school children. Some of them are aimed at higher, like 11, 12, university level science as well. So check it out. Right now, why don't I just do a quick simulation? I'll show you the kind of things that you can do over there. So let me stop sharing over here. And I will share this screen. So if you go to that website, which I have given you the link to, you don't have to do it right now. You can just look at me right now, but feel free to play with that simulator later. So what this does is, on the right hand side, you can make various functions over here. And so in the upper graph, by the way, can all of you see this?
Yes, Professor.
So over here is the function, and down over here, it will show you what the derivative is. So first, let me choose the constant function. So you can see that when a function is constant, it's not changing. So its derivative is going to be 0. So the derivative given over here by this red line is always going to be 0. No matter what the value of f is, constant function always has 0 derivative. What if instead I took a linearly increasing function? Now this function is increasing, but always at the same rate. So the derivative for this is going to be a constant. As I increase the slope, the derivative increases, but remains a constant. Slope is decreasing, slope becomes 0. Now slope becomes negative. You can take other complicated functions as well. What is happening here? So initially the function is not changing at all. So the derivative is 0. Then the function starts to increase. So the derivative goes up. At some point, after having increased, the function becomes flat at the top of the hill. Means the derivative has again become 0. So the derivative has become 0 again. And then it decreases. So the derivative is negative now because the function is decreasing. And eventually again it becomes flat, therefore 0. You can do it with sine waves. Oh dear. What is happening over here? So first, the function is not changing. So derivative is 0. Now over here, the function increased suddenly, very drastically it changed, which is why the derivative suddenly became very high. Then again over here, it is not changing. So the derivative became 0. Now it decreased dramatically. So the derivative has a very high negative value. Then again flat, and so on and so forth. And you can also do your own thing. And you can try and explain these various features using the definition of the derivative. So feel free to play around with this once later at your leisure. It'll give you a good feel, a good intuitive feel of what a derivative actually means. Let me quickly list out certain derivatives for you, which you have probably seen before. So the function and its derivative with respect to x. If the function is a constant function, then the derivative is 0. If it is a linearly increasing function, then the derivative is just k. If you have a quadratic function, then the derivative of that is 2x. In general, if you have x to the power n, then its derivative or rate of change is given by n x to the power n minus 1. Sine of x gives you cosine of x. Cosine of x gives you negative sine of x. Log of x gives you 1 over x. E to the power x, interestingly, gives e to the power x. In fact, this is one of the ways of defining the exponential function. It is the function whose derivative is equal to the function itself. Then there are some interesting results, like suppose you have two functions f and g, and if you want to take the derivative of f times g, then this is given by f of x times derivative of g plus derivative of f times g. So you take the derivatives one at a time. If you have not the product, but the ratio of the two, then this becomes g df by dx minus f dg by dx divided by g square. Because if you have a sum of two functions, then derivative is just their sum of the derivatives. So these are some of the basic rules of derivatives, which we will not define over here, but they are very useful and you will probably use them at some point. Okay, so we'll stop here for today. Any questions?
When will we start the physics part?
So I am hoping in the next lecture to finish the maths.
Okay.
And
Okay.
then, so next week I think we'll start the physics.
Okay. And will you be giving us like assignments or problem sets or something?
Yeah, so I think I'll give you the first assignment sometime later this week.
Okay.
And you will have 1 week to solve it and give it back.
Okay, thank you.
So by the way, so on the Canvas page, I have said that I'll give you 10 points worth of quizzes, but I'm also toying with the idea of instead giving you a 10-point writing assignment. Do you have any preference as to which one you would prefer? Okay, if not, then I'll think some more about it and then decide by myself. Any other questions? To those of you who had not done maths before, how is the speed?
It's fine. It's okay for me.
Okay. Okay, if there are no more questions, we'll stop here. And you have a couple of minutes before your next lecture. Okay, see you in a couple of days.
Thank you.